There are more than 150 million relays in the Bell system. They are well designed and well made. Together with adjustment procedures developed to secure the best performance, relays are durable, reliable, ready to do a good job, provided we adjust them properly when they're in trouble. Over at the Bell Laboratories, an engineer is going to show us how U and Y-type relays are better than the other flat-type relays.
Let's look at a U relay that is properly adjusted. First, we'll examine the armature bounce with the help of high-speed photography. We'll do this twice, so the first time, watch the armature. The armature operates. Now we'll release the relay. See it bounce against the adjusting nut? Now this time, watch the springs. See them vibrate? This spring vibration is always present, but it will not cause trouble if the relay is properly adjusted. If you look closely, you will see that there is no false contact operation. It's the result of changes in armature design and careful proportioning of the stationary and movable springs. This improvement was necessary to meet the more exacting requirements of the newer switching systems. And now just a word about the Y-type relay, which was developed to provide slow release characteristics. From outward appearances, it doesn't look very different from the U-type. This drawing shows the difference in the magnetic circuits. Notice the two stop discs welded on the armature of the U relay. These discs are non-magnetic and introduce an air gap, thus permitting the relay to release promptly. However, on the Y relay, the discs are omitted to make it a slow release relay. Instead, a raised surface is stamped into the armature. This is known as embossing and serves a very important purpose in the mass production of Y relays. The angle with which the armature meets the pole piece varies between relays. In this exaggerated view, you will notice, however, that the armature rests against the pole piece with a one-point contact due to the embossment. This provides greater uniformity in the release time of Y-type relays. To increase the release time and provide some degree of variation for various circuit conditions, copper or aluminum sleeves of different thicknesses are placed over the core of the relay. The thicker the sleeve, the longer the release time. Some people find it hard to believe that there is actually much difference in release time between a fast release and slow release relay. In this high-speed shot, let's compare the U relay on the left with the slow release Y relay on the right. Notice there isn't much difference in the operate time. But now watch them release as current is removed from both windings at the same instant. The Y relay remains in its operated position for some time after the U relay has released. But remember, the Fast-Tax camera has slowed the action 200 times. The requirements for adjusting relays properly are right here in the Bell system practices. They are developed to secure good performance with the least headaches for the maintenance man.
And that's something any central office man would be glad to talk about.
That's right. Occasionally, a relay fails. When it does, the best medicine is a careful job of adjusting. All adjustment procedures are right here in the Bell system practices. Unless we follow them, the value of careful relay design and manufacture can be lost. I'm not going to try to cover all of these requirements, but I would like to show you some of the things that cause many of our relay troubles. The first thing I'll show you with this movie projector is dust and lint on relay springs. This can happen in a central office when the covers are left off. It's what we call man-made trouble. Relay covers should be removed only when absolutely necessary and replaced as soon as possible. Here's a drawing from the practices showing one of the adjustments that is important to prevent contact chatter. There must be proper clearance between the ends of the spring studs and the adjacent springs. To check the spring stud clearance, the number 510C test lamp is a very helpful tool to magnify and illuminate these close quarters. Here's a relay properly adjusted, except that there is insufficient stud gap at this point. When a relay does not have enough stud gap, this is what happens. Watch the spring action as the armature bounces. See the contact open? Well, here is the same relay with proper stud gap. The contact chatter has been removed. Contact chatter may cause circuit troubles and is sure to result in excessive contact erosion if the contacts carry current. This drawing shows one arrangement of a typical spring pileup on a U relay. Springs A and D press against the spring stud, which rests against the armature and provides what is called armature back tension. This tension must be at or above the specified limit, for it is one of the things that affects armature bounce. But here's another important thing. The tension of the spring pileups must be balanced within specified limits, or we would have a misalignment of the armature. Like this. Such a relay would be unbalanced, would not meet requirements, or perform properly. And while we are talking about armature back tension, the use of the 70 type gram gauge certainly deserves consideration. But it must be used properly, or an incorrect reading results. Place the reed flat against the armature at a point even with and behind the adjusting nut. The reed must lie in the same plane as the armature. Now rotate the gauge, making sure the reed remains flat. When the armature just leaves the adjusting nut, the gauge will show the tension. If a pushing motion like this is used, the reading will be wrong. Another important requirement of relay adjustment is contact make, commonly called follow. This relay is properly adjusted. As it operates, watch the deflection of the moving springs after their contacts make against the stationary or spool head springs. This is an indication of contact follow. Proper follow creates adequate pressure. Contact follow also provides an allowance for contact and spring stud wear before failures result. Let's look at this brake-make-spring combination that is not properly adjusted. Note that the lower contact of the bifurcated spring makes before the upper contact breaks. The same contact bunching happens as the relay releases. This may cause faulty circuit operation. Now, here is the way the contacts should operate. The brake contacts open before the make contacts close. No discussion about relay adjustment is complete without a word about contact erosion. Watch the arc that occurs on the top contact of this relay when it releases. This will cause severe contact erosion that may result in contact locking or loss of adjustment due to loss of contact metal or its transfer from one contact to another. Here are some examples. These are silver contacts. See the large buildups? They may snag in the holes of their mating contacts and fail to open. These are palladium contacts that did lock. Eroded contacts require maintenance. If they're not too bad, the buildups can be removed with a 527A tool. The proper blade must be used with care so as not to remove useful metal. Here are the silver contacts we saw a moment ago after treating with a 527A tool. When the contacts are too far gone, new contacts must be welded on with a contact welding tool. And in all cases, the relay must then be checked for adjustment. Of course, contact protection networks like these 181 types help to reduce contact erosion and troubles. Here are some 184 types. These networks, a condenser and resistance in series, help to reduce the momentary voltage surge that occurs when the relay contacts open. The effect of contact protection can be shown very clearly on an oscilloscope. This is an electrical picture of the arc resulting when contacts do not have protection. This line at 0 volts shows the voltage across the contacts before they open. At this point, the contacts open. Note the high voltage peaks. Arcing of as much as 3 amperes occurs during this period and continues until the voltage drops. Now here is a picture of an identical circuit with protection. The line shows 0 volts until the contacts open. In this case, however, notice how the protection network reduces the voltage surge so that no arcing occurs. But the secret of good relay performance is proper adjustment. Understanding the importance of following the procedures in our practices is basic if we are going to avoid relay troubles. Of course, the Bell Laboratories engineers are always looking for improvements. Take the problem of stud wear.
Yes, stud wear results after millions of operations of the relay. As the stud wears down, contact follow becomes less. Contact pressure decreases. And eventually we have contact chatter and failures. We have improved this condition by a new stud material of synthetic rubber and graphite that reduces wear. Now, hinge pin wear is a condition that may cause trouble on relays that operate 100 million times or more during a normal relay lifetime. About 15% of the relays in the average office work this hard. Here is one that shows what I mean. Notice the movement of the armature due to the hinge pin holes becoming enlarged. The armature drops down and rubs on the spool head. This may have a serious effect on the operate and release time. On new relays, we've overcome this by substituting a spring hinge. However, we have kept the advantage of the overlap between the armature and end yoke. Here's a condition that sometimes develops on the fast-operating U-type relays. These stop discs on the armature finally penetrated into the core. This affects contact follow and increases release time. We have been able to practically eliminate this condition by using a different metal for the stop discs on hard-working relays. For relays that develop this condition in service, we have a plastic separator that slips over the core. Speaking of separators, here's one developed for another purpose. I'm going to show you two Y relays. They're the same in every respect, except that the one on the left is new. The one on the right's been in service for a long time. They are both operated. Watch them release. The relay on the right is too slow. It has developed what we call aging of iron parts, and eventually may not release at all. Its magnetic properties have changed. This condition has been corrected in present relays by using hydrogen annealed iron during manufacture. However, when the condition occurs in the older relays that are already in service, it can be corrected with a magnetic separator. The Bell system practices explain how this should be done. And here is an interesting little gadget called a motion limiting washer. It was developed to prevent the breaking of coil leads. The reason for this breakage had us puzzled for some time. But this is the main cause. Notice the slight movement between the winding and the core? This vibration, occurring mostly on fast-operating U relays, sometimes causes the coil leads to break from repeated bending. However, this washer is now slipped over the core during manufacture and sealed to the front end of the coil, thus reducing coil vibration. And now, one more thing. I know you've all seen the instructions in the practices about magnetic interference between relays. Here are 8 U relays mounted around a Y relay, as you might find them in any office. When adjusting a relay to meet circuit and timing conditions, the adjustment may be critically affected by magnetic interference from adjacent relays that are operated. This may be hard to believe, so let's run a test. This 35-type test set will give us the current reading on this center Y-type relay. Now here we have a timing set that we will use later. It is designed to show the actual operate and release time. First, Let's get readings of the release current values. I'll operate the center relay. Notice that the adjacent relays are not operated. I'm not showing the operate values because magnetic interference has a greater effect on the release. There, it's released. Now watch the center scale. The release current value is about 7 mils. Let's put this down so we won't forget it. Now I'll energize the center relay. And relays 2 and 8, directly above and below the center relay. Watch the release current value, again on the center scale. 10 2/10 mils. Now I'll operate the center relay and all adjacent relays. This time the reading will be on the top scale. It is 20 mils. Note the increase in current values due to magnetic interference from the adjacent relays. Now let's use the timing test set to see the effect of magnetic interference on release time. Each microampere on the scale is 1 millisecond. So a full scale reading would be 100 milliseconds. The first test will be with all adjacent relays unoperated. The center relay will release as I throw this key. Release time is 72 milliseconds. Now I'll operate relays 2 and 8. The release time is 54 milliseconds. Now let's see what happens when all adjacent relays are energized. The release time is now 32 milliseconds. In most circuits, relays operate as a team. Therefore, timing is extremely important. And yet, as you can see, release current values and release time are very definitely affected by adjacent energized relays. The same thing would happen in varying degrees if other combinations of adjacent relays were energized. This is very important to know, for it may mean that a relay you think you have properly adjusted will not at all times meet the circuit requirements. The circuit requirement tables on the circuit drawings are prepared so that satisfactory operation and release of relays is ensured, provided the instructions in the Bell system practices are carefully followed.
That's the story, all right. But actually, only a small percentage of the relays in an office ever develop trouble and have to be adjusted. So long as they keep on working, leave them alone, because tinkering can cause a lot of relay trouble. But when they do need adjusting, remember, do the job right according to the book.